Hello. Albert Einstein said among the most difficult problems in all of physics is the Earth's magnetic field. My name is Michael Doran. I'm a California attorney, and I'm going to argue that the Earth's magnetic field is actually among the most difficult problems in all of biology. Today, it's kind of a subset of that. I want to talk about a seismic clock that was discovered outside of or inside an island in the South Atlantic Ocean off the coast of Africa. The view for a long time was that the heart was the seat of consciousness. That's where the bleed out treatment of George Washington and other famous people, that the doctors of the time thought that blood was where the seat of consciousness came from. How we were animated was the blood, and that the heart was the center of it. Of course, now we know that the brain is the seat of our consciousness and awareness. We know now that, of course, the heart is a bunch of nerves and muscles. And what's interesting is that there's acoustics to the tissue so that you can send a shock to the heart and it will restart itself at time under certain circumstances. The acoustics of the shock, or the shock, brings the heart back into acoustics of life. Computers have clocks inside their processors. They won't function without a clock. And so in my view, the living Earth is a little different from that. It began with nucleotides and cloud droplets, and they had to have a clock or a frequency to enable for those nucleotides and cloud droplets to communicate with each other, so that the nucleotides could be both a feedback and a model. Collectively, the nucleotides and the clouds were a model. Over time, the nucleotides became more complex, but also the geography and the morphology of the Earth became more complex. And the problem that was being solved was the Earth's magnetic field in relation to the inputs from space weather. So to solve this problem of the Earth's magnetic field, there's two parts. There's the space weather part, whether you're talking about cosmic rays or changes in the solar output, whether it be a flare or an X-ray, or whatever the sun is doing. But also the Earth, inside the Earth is a solid metal core and then a liquid metal that kind of surrounds that, and that produces a magnetic field. What the state of the science is that there's nothing that influences the inside of the core, that the magnetic field sort of is a stasis. It is what it is, and we just adjust to it. In my view, what I'm trying to explain is that the Earth is alive. It communicates in electrical terms, and that magnetic field is actually a dampened result of life. That electrical currents will melt the subterranean and alters conductive pathways and so forth. One of the biggest mysteries in seismology, I guess, or I don't know if that's the correct word, but when it comes to seismic activities, is this seismic clock. The seismic clock is found off the coast of Africa, and pardon my drawing, but here's my drawing of Africa, and it's not a very good drawing, but So the seismic clock is located right here, and just get over on this side. Maybe I'll block some of that light. And it's just off the coast of Guinea, and it's on an island, and it's been discovered to be a volcano that every 26 seconds it vibrates. There's seismic activity associated with it. Now, again, pardon this poor drawing, but if I were to draw South America over here, and then Australia over here, what you see this time of year is a bunch of lightning that kind of gathers over the land, more or less. And 90% of lightning occurs over land. And the reason for this is has to do with the leads that produce lightning. And that is, you have a cloud, you have daytime convection, instability, and so if this is a cloud, and you have convection, and the cloud rises during the day, and friction bumps the ice crystals and all the materials inside the cloud and causes charges to separate. Now, if you're over land, then there's no places for charges that accumulate inside the cloud to go, or any organization to occur, and any way for those charges to, the energy inside the charges to go anyplace. So what you end up having is leads that or plasma that is created in the air, and then once it's strong, that the leads are long enough, then the currents will flow to the land, and then you get lightning. When you have a cloud over the oceans, it's a different problem. And what we're seeing with the clouds over the ocean is that you have these undulations forming where you get these capacitive relationships between the charges in the clouds. I'll say you have a positive charge in the cloud and a negative charge. Then over the ocean, you'll get a negative charge and a positive charge. And you get waves where the energy that is accumulated in the cloud is dispersed, and so you don't have enough potential difference for the leads to form. So 90% of lightning occurs over land. And on top of that, because Africa has a very large head to it, and then it narrows off as the intertropical convergence zone changes from the season. So here's Africa, and what happens is during the tropical storm season, the intertropical convergence zone is like that. It's over the above in the fat part of Africa, and it's more over land. So you get you get more lightning during either the spring or the fall when it's over the wide part. When the intertropical convergence zone falls south and it's over in this area, there's two things that happen. The first thing that happens is the Southern Ocean, which is here, starts to act as a common between South America, Africa, and Australia, and a little bit into China. And when that occurs, you get bunches of lightning that are organized in a north-south direction rather than horizontally. And also there's less land, so there's less lightning in general. And so what has been observed is that during the CV season, the most stormy part of the season, that is when the that is when the seismic clock is the most intense. And one theory is that the seismic clock is caused by wave action, but that doesn't make any sense because waves would be most intense when the intertropical convergence zone is actually by that volcano. And the opposite occurs is that when the intertropical convergence zone is over the wide part away from the volcano that produces the seismic clock, that's when it's most intense. And while there's CV storms that form here and are strong and do produce strong waves, the western part of Africa is going to block those waves from being anywhere near the volcanic clock or the seismic clock that's in the volcano. So what I want to show you now is I'm going to draw a volcano and to think about it in a totally different way, in an electromechanical way. So again, I'm not an artist. Let's do it this way. This is a rough drawing of a volcano. And what you have is a part inside the volcano where the magma comes from. And it's kind of like a bell. It's going to capture the vibrations coming from down beneath the earth. And you have, because the volcanic rock is hot, it's more conductive. And also, because of the shape of the volcano, it's going to be able to carry and capture the vibration that's occurring. The vibration, in my view, comes from deep inside where the lightning that is occurring during the CV season and the couplings over the ocean, which are very strong, the most electrically interesting places on Earth. It's the low impedance place on Earth, because again, you get these organizations. This time of year, it's just the opposite, where Africa will have undulations that are sometimes north-south. Like today, the undulations were literally north and south. One that was just off in the interior of Africa, but just right next to the undulations. And then one that was an undulation that was by Italy. You can see, if you go to null on the web, where you look at the surface winds and then you blur it a little bit, you can really see these undulations where the clouds get organized by Schumann resonances or by how, when lightning strikes, it's like taking a hammer to a bell. The bell starts to resonate. Well, Earth's magnetic field is the same way. When lightning strikes, that pulse of current agitates Earth's magnetic field, and when it does agitate the Earth's magnetic field, it causes changes in potential difference that then result in other lightning in a crescendo or an order to lightning in general, and you get these Schumann resonances, which are well observed. It's textbook stuff. What I'm suggesting, clearly from the evidence, is that not only are there resonances, but the resonances act in an electrical mechanical way, just like an electric car or any other electrical mechanical apparatus, that the changes in the resonances result in mechanical or vibrations that are then picked up in the caldera of the volcano. And since it's subterranean where those currents are flowing, it doesn't matter whether it's off the coast or on the coast, you're going to get a pickup as you're going down into the earth where the lightning strikes over the wide part of Africa. It goes down and then it causes this electromechanical thing, and then it goes back up and gets captured by the volcano. There's another place on Earth where a seismic clock type of behavior has been seen, and that's off the coast, or I'm sorry, in the volcanoes in Japan. So again, I'm sorry about the poor drawing, but let's say that this is, I don't even really know what Japan looks like, but here's Japan. A lot of times you'll see these Western Pacific storms. They'll track along the Japanese coast, just like, in a way, like the CV storms are coming from lightning, which is power couplings. You'll get regional lightning in the area, and then a kind of a cross section of Japan would be, you get the ocean plate going underneath, and here's the Marianas Trench here, and then you have basically Japan proper, and it's going, the ocean plate is going underneath Japan, and here's your volcano up here, and so you're going to get lightning in the China area and land generally, and then your tropical storm is up over here, and as the coupling is picking up the lightning and the resonances, it's causing electromechanical movements down inside the earth, and it resonates in a way that it's picked up by the volcano, and they're picking it up, and they're going, what the heck's causing this? We see that it's active when there's storms, but when there's storms, there's essentially more electrical activity closer to the volcano. Okay, thank you for listening. Again, have a good one.